Okay, so this is fourth lecture. Last time, so before doing new stuff, let me just finish a couple of things that was left from last time. One was this, about, we wanted to know that determinant, say from un to u1, this induces an isomorphism on pi1 level. So induces a map that from pi1 of un to pi1 of u1, which we know is isomorphic to z. So, and then the thing is, we want to know that this is actually an isomorphism. So as a result, then we can conclude that pi1 of un is isomorphic to z for all n, actually. And this is what we needed in order to finish this proof of Goldberg-Klein. So to prove this, you can just use this exact sequence, 1 sun, because the kernel of pi1, the kernel of determinant is sun, the special unitary group, right? So this is un, and by determinant, you go to u1. So this is a group extension. Maybe even I don't need it, but I think this extension is actually a split. So there is a map in this direction, S. So what is this map? So S sends e to the I theta to this matrix, unitary matrix, e to the I theta 1, 1. So it's a splitting of determinant, as you can see. Anyhow, so this induces a fibration. You get a fibration. So the fibration is sun, goes to un. So the fiber is sun, and then the map is maps to u1. So this is the determinant. Then what you can do, you can use homotopy exact sequence for fibrations. Then use homotopy exact sequence for fibrations. Then all you have to know is that sun is actually simply connected, plus sun is simply connected. You can use these two things to conclude that actually this determinant induces an isomorphism from pi1 of un to pi1 of u1. So this is an isomorphism, and this finishes the proof. So this I won't prove. You can prove it in different ways. So, but it's good to see at least for n equal to 2 what happens. So for this one, for n equal to 2, we have su2, which, as you know, is isomorphic to s3. You can also see it as unit quaternions. And in this case, you can see that this is simply connected because S3 is simply connected. And in fact, SU2 is universal cover of the rotation group, special rotation. So this is a universal code. So one way or the other, you prove SUN is simply connected, and then you show that then it implies by these general things that actually determinant is a
yeah. So
yeah.
So this I was commenting last time. So for SUN showing it simply connected, you just act it on S2n minus 1. So it acts on Cn. So it lives. I'll think of Cn as R2n, and the sphere there is S2n minus 1. So I'll act UN on S2n minus 1, and it's a homogeneous space with UN minus 1.
Okay.
So now I have another fibration. So now I look at that long exact sequence in homotopy. So I'll get pi 2 of S2n minus 1 to pi 1 of SUN minus 1 to pi 1 of SUN to pi 1 of SU2n minus 1.
Yeah.
Both sides vanish, and then inductively I will show that it is 0.
Yeah. Yeah. I mean that you can do it that way exactly, using similar ideas for a different vibration. That's right. But yeah.
You'll realize homogeneous
spaces, so you have a lot of tools because they're homogeneous space. Okay, so that's good. Of course, a similar proof shows that GLNC is also simply connected. Similarly, not simply connected, sorry. I mean, what I mean is you can show that using more or less same idea, that determinant from GLNC to GL1C, which we know is C star, right? Non-zero complex numbers induces an isomorphism. An iso, so this iso, so it tells us that pi 1 of GLNC is isomorphic. And okay, so that's what we need in order to finish the proof of Goldberg-Krein, right? So the corollary is Goldberg-Krein. So remember, so I don't recall the setting, that's what we did in previous lecture. So basically we wanted to show that index of T phi, or well, I think I used T phi, is equal to minus winding number of determinant of phi around 1. So phi was from S1 to GLNC, right? GLNC is a continuous map, and well, this T phi, of course, is the Toeplitz operator with symbol phi. Right, so this is so yeah. I mean, the original you remember the original northern index theorem was for n equal to 1. But you can exactly take the same route, and then by this calculation, this determinant of phi, except the homotopy class of your map, the two sides are homotopy invariant, and then you're reduced to actually checking the one-dimensional case, which you know is true. So this basically proves the result. So that's so we need this calculation, a little bit of homotopy theory. Will finishes the proof. Any questions about this? Okay, so that's good. So before moving on, there is okay. So because yeah, okay. So there's another index theorem I'm going to recall along these lines. It's similar, but it has a little bit of different flavor because you're going to see really differential operators. Here there is also a differential operator in the background. So let me recall that. So for that, I need a little bit again algebraic topology like this. So what I need is something about cohomology of UN, or in fact, or GLNC. They have the same cohomology groups because this is really a maximal compact subgroup of GLNC, and in general, we know that maximal compact is a deformation retract of the big group, so they have the same cohomology topology because one is the deformation retract of the other. So now the question is, what is cohomology of this guy, H star of UN? In fact, we know it's cohomology with integral coefficient even. So let me tell you what it is. This is just exterior algebra on these generators C1, C3, C2n minus 1. So, so this is exterior algebra, but these generators are odd cohomology classes. And I can call this CI is transgressed Chern classes. These are not Chern classes because Chern classes are even cohomology classes. They are cohomologies of somewhere else, of Grassmannians. But these are related to those Chern classes. They are, if you write down some, again, kind of exact sequence, not exact sequence, a spectral sequence for cohomology of vibrations, which is more complicated, then you will see the relation between these CIs and the Chern classes of Grassmann. But that's what not we are doing now. So I'm just writing this. And in fact, this is isomorphic to, there's another way of thinking about it. This is really isomorphic to cohomology of odd spheres, multiply. 3, S5, S2n minus 1. Okay. So why this, I'm not saying this space product is homotopy equivalent to UNs. That's not true. But there is a sense that it makes sense to write it like this because of much more general result due to Cartan and Hopf, which you can show that cohomology of Lie groups like this, compact connected Lie groups, always are isomorphic to cohomologies of products of odd spheres. That's what. But anyhow, so in this case, so there is a Theorem realization of these things. Theorem realization. So by Theorem realization, I mean, I can write now some differential forms over UN or GLNC that are representatives of these things. So these differential forms are these ones. So, so C2k minus 1 is equal to some constant, some important constant, but I don't mention what it is. I'll put 2k minus 1. Trace of, so let me write it like this, G inverse dg to the power 2k minus 1. Okay, so these differential forms, so where this leaves, this of course belongs to, it's a differential form of degree 2k minus 1 on UN, right? This one. So if you have difficulty understanding this, just think about it like this. There is this map G from UN to n by n matrices. So it's a matrix valued function. You differentiate it component by component. So when you multiply, take inverse of this, and then you multiply, right? When you multiply, you're going to get a matrix of one forms. raise it to power 2k minus 1 using matrix multiplications and exterior products of forms. Then you get a huge, again, n by n, yeah, matrix of 2k minus 1 forms, and take trace of that. Okay? So then this is a 2k minus 1 form. And what you can check about these forms actually is the following. First of all, they are closed.
Sorry, what is G?
Yeah, so I was kind of describing G by in words. G is the tautological map in a sense. G from UN to Mn of C. Basically, G of A is equal to A. So G is doing, it seems it's doing nothing. It just components of the matrix. It's the matrix that represents the group element, right? Okay. So then by DG, of course, is a matrix of one forms on UN, right? So this belongs to, let me put it like this, Mn of omega 1 of UN, right? Omega 1, yeah. Omega 1 of UN. And then same with G inverse DG. And then you can use, as I said, combination of product here, product there, G inverse DG to power 2k minus 1 belongs to Mn of omega 2k minus 1 UN. Okay, and then you take trace. So that's the. Now, the claim is that, first of all, I mean, the first exercise, this is not difficult, is that you can check that this is a closed forms. That trace of G inverse dg, just write it like this, is closed. This is not difficult, you can check using basic properties. And so for fun, you can also prove that if you take the even ones, so 2k is actually exact. So by this method, you're not going to produce some interesting even cohomology classes because these are exact. But of course, it's a theorem. I won't prove it, that these are generators of the cohomology. And even more interesting, you can fix these numerical coefficients, some 2 pi powers and factorials and stuff like that, such that they are actually integral cohomology classes. Okay, so this is, so with suitable constant, they are integral differential forms. Integral cohomology. It doesn't matter for us for now. So we need this just to move on. Any question about these forms? So I think later on when we do characteristic classes, we are going to see the even versions of this, but these odd versions are also very, very interesting. They appear in many places. Okay, so now let me then go to explain the last index theorem before moving to general stuff again. So this index theorem, so let me get a chalk first, good chalk. Okay, so so what's the setting? Now we're going to work on this Tn, which is U1 plus U1 n times. So that's n torus. And then we are going to pick some matrices, say n matrices. Gamma 1, gamma 2, gamma n that satisfy the Clifford algebra relations, right? So they satisfy gamma I, say, oh, gamma mu plus gamma nu, gamma mu is equal to 2 delta mu nu. So these are Clifford algebra relations. Well, I said pick matrices, but I didn't say what size. So n by n, say. I won't tell you right now what n is, but imagine you can do such a thing. Imagine there is a n, index n, and there are little n, n by n matrices that satisfy this relation. Then you can define this Dirac operator, right? This is one incarnation of many different incarnations of Dirac operator for us. So this is Dirac operator D is equal to I sum gamma. Oh, I made a mistake. I put it down here. Maybe I should put up. Sorry. I put down here now. It doesn't matter. We got this up. Okay, so this is like gamma mu d mu. So you can also write it as using Einstein summation convention as I gamma mu d mu. So of course d mu is just d dx mu. Okay, so now this D, this operator D, is acting on matrix valued functions on the n torus, right? So this D now, this Dirac operator, goes from C infinity of Tn, and with values, well, did I say matrix valued functions? No, I mean vector valued functions, Cn to itself, right? So this is a smooth vector valued functions on Tn, and the way this acts, well, it just acts like this. So this is D, and if you have a column matrix or vector like that, so this is I gamma mu d mu of this. So you apply these partial derivatives to these things, different components. You get another column matrix, and then you multiply by this n by n matrix. You get a column matrix. So that's the way it is, right? Okay, so good. So we have that. Now, of course, this D you can check that D squared is minus Laplacian, right? Well, this is Laplacian tensor again, some n by n identity matrix. So, I mean, this is a scalar Laplacian, but then you have to inflate it to vector Laplacian, which is I denoted by this. So that's not. Okay, now this operator D, in fact, is self-adjoint. So provided you choose your gamma mu's in the right way. So I'm assuming you're choosing your gamma mu's are self-adjoint. So if this is the case, because this is self-adjoint and then I d mu is also self-adjoint, then you can show that this D at least formally self-adjoint, but in fact, technical sense is also self-adjoint.
So I had a question.
Yes, yes.
So any reason why you're considering maps to Cn and not say Rn?
Not what?
Not Rn. Why are you considering maps to Cn and not Rn?
You can do that, but Rn. Okay, so yeah, that's a fair question. I mean, these gamma mu's usually will have complex components. It's not. Usually, they will be complex matrices, especially if you want to have self-adjointness. So then, if you go to Rn, you end up out of Rn even.
Mm-hmm.
So these spinors are complex objects. Although, I mean, there is also some real aspect to it, like Majorana spinors and stuff like that. But just to be safe, let's start with Cn. Yeah?
Okay.
And because very soon, actually, we are going to work with, I mean, exclusively with complex vector bundles, not just real vector bundles. I mean, complex board, in fact, is simpler, and that's what we want to start everything with in that simpler board, right? Real is always more complicated, right? So we want to start with a simpler case.
Sure.
Okay?
Yeah.
Good. So then what we can do is the following. We can just look at the spectral projection onto, so let P chi of, so just write it this, yeah, D bigger than equal to 0. So that's a spectral projection onto positive or non-negative eigenspace. So this operator, actually, you can show that because it's self-adjoint, it has positive eigenvalues and negative eigenvalues. In fact, this is more than self-adjoint, is what I'm saying. But just cut down the negative ones and pick the positive, the space, the subspace of the L2 Hilbert space. This is, by the way, inside L2 of Tn and Cn. Like in the Toeplitz case, we work with C, continuous, smooth, and L2 functions. Here the same. So you cut down those negative eigenspaces, just look at positive ones. And so this P is the projection onto that space. So this is, we are mimicking this Toeplitz construction in this setting, right? So that's this one. Okay, so now, again, we can just take y from Tn to, say, GLNC, the same n as here, continuous map. And then you get this Toeplitz operator, in this case, T phi equal to P m phi, P phi. So this is exactly the analog of the Toeplitz operator construction. We started with n equal to 1 on the circle, right? So this is this projection, multiplication by this symbol phi, and then you have to project down. So, but in this case, of course, everything is much more involved because, first of all, dimension of this background space is higher than 1. So far, we just work with n equal to 1. And the space positive, the projection P is defined using positive eigenspaces of this this Dirac operator. So, but in the case of n equal to 1, you know, we check that actually when we had just ddx, right? There was only one differential operator, and we looked at the positive eigenspace of that. That's what defined this Toeplitz operator, even in the case of n equal to 1. So it's completely similar to that. Now, so when n is odd, so this is an interesting index problem when n is odd, and there's an answer to this, the index problem in this case, which is interesting. I just mentioned, and then I will, hopefully maybe we can go back to that sometime. So there is a theorem. I believe this theorem is due to Proudhon and Schulz-Bos. This is a more recent theorem, I guess. Schulz-Bos. I hope my spelling is correct. So this is Emil Proudhon and Schulz-Bos. So the result, it computes this index. So first of all, let n be even, odd. Then index of this operator T phi, again, is a Fredholm operator. You can work like before and show that this is Fredholm operator, this Toeplitz operator, is equal to actually integral over Tn of the pullback of C2n minus 1. So which one should we take in this case? So let n be equal to C 2k minus 1, where n is equal to 2k minus 1. Okay. So you pick an odd number of the form 2k minus 1, then that chain class, integral chain, it's not chain class, it's this transverse chain class, that generator that we had. So you pull it back, integrate it over Tn, then this is the index. So remember this C 2k minus 1, I erased it, but here is really just alpha, some numerical constant, times, trace of the inverse dg to the power 2k minus 1. So that's what we had. So for k equal to 1, of course, this is g inverse dg, and this is the case of original index theorem of Noether and Gober-Krein. But here we are using the higher analogs of winding numbers. So these are, you can think of kind of higher analogs of winding numbers, which work over tori in higher dimensions. So that's the what we have for examples and motivations for index theory. So these are simplest examples really, and actually these examples were not the motivations for Atiyah-Singer. So I will tell you what the motivation was. But educationally, I mean, pedagogically, I think that it's useful to know these examples to practice with them. Okay. So maybe is a good time to ask if there is any questions or comments.
So when you again speak about Fredholm here, in the case of,
yes,
in the case of the operator D, so again, don't you need that to be a complete space, or don't you have to complete C infinity Tn there? You need to extend it to the completion of C infinity Tn, right?
This operator, it does. Well, this operator is okay because, yeah, I mean, here is, yeah, I mean, this D though, I don't need it. I don't need this D I don't need any extension of it. I just use D to define this projection P. Remember? So this projection P is like this. You just take these positive eigenspaces and complete it. Okay?
No. So for the map T5,
T phi is okay. It acts on L2 because it's just, this is a continuous function. And if you have an L2 function, multiplied by continuous function, you get a bounded function. So what I'm saying is that this T phi actually is a bounded operator. From, yeah, I mean, this, maybe that's what you meant. It goes from L2.
Yeah.
Yeah, sure, of course. To itself, right.
Oh, you take the L2 completion, is it? You won't take like the Sobolev completions or something?
No. There is no Sobolev, not yet. I don't need it yet, but it will come. We have to use Sobolev soon. But you see, the emphasis here is on this T phi. In these Toeplitz operators are themselves bounded operators. So we don't need so. But this D, if you want to think of D as a bounded linear operator, then you have to go into Sobolev scales. That's we will see that. We'll see that soon. But this just yeah, it's a different flavor in this case, indeed. Yeah. No Sobolev theory needed yet, but we will need it strongly soon.
Okay.
Any other comments or questions? So I'm worried that my things is power is dying, but that's okay. So so now let's do one last thing. So that's about topology of Fredholm operators, say Fred H. So what do we know so far? By the way, H is a Hilbert space, is infinite dimensional, even separable if you want, but infinite dimensional and complex. So that's what, these are always our standing assumptions about H.
Sorry, Masood, just before you proceed,
Sure.
can you comment on what happens in the even case?
This is all? Oh, it's zero. The index in the even case is zero. It's not interesting.
Okay.
So yeah, that's a good question. In this case, we don't get anything interesting. The index is zero. The only thing that that's, yeah. Okay. You may enjoy yourself actually proving that index in that case is zero. It's not difficult. Yeah. Okay. So what do we know about topology of Fred H? So space of Fredholm operators. From H to H. So we just said that it has infinite number of, first of all, it's open in L of H. It has infinite number of components, and these components are defined, are indexed using index. So that's two uses of the word index, right? So the components are indexed by index, but in two different senses, right, of the word index. So, but I already asked the question, what do we know more about this topology of this? In fact, there is a very deep theorem which goes a long way to describe the topology. So this theorem is, so let me write it here and then explain. So this theorem is Atiyah-Jaenich theorem. So the result says that for any compact space, compact Hausdorff space X, we have a canonical isomorphism between this set X to Fred H with K theory of X. So let me explain elements here. So by this thing on the left-hand side, we mean the set of all continuous maps from X into Fredholm operators up to homotopy. So these are homotopy classes. families or continuous, I would say, families of Fredholm operators parameterized by X. So first of all, we have this continuous families of Fredholm operators parameterized by X up to homotopy. It's a set, that's what we know. And it's in one-one correspondence with K-theory of X. So let me recall you, K-theory, this is complex K-theory. And it's, now the idea in this case is, the idea in this case is, okay, so K0X is complex K-theory of X. So that is the group completion or Grothendieck group. By definition, is the Grothendieck group of the set of isomorphism classes of complex vector bundles over X, of set of isomorphism classes of course, finite dimensional vector bundles over X. Okay? So this is an abelian group. So it would be nice to know that actually isomorphism is somehow the isomorphism of abelian groups. In fact, that's the case because you can define a group structure here, which is just if you have a family like F1 and F2, two continuous maps from X to Fred H, then you can define F1 plus F2 to be, the addition is defined by multiplying these things, but take class of F1 times F2. This defines an addition, and you can show that actually this is an abelian group. Structure on the left-hand side. So the statement is that, in fact, this canonical isomorphism is an isomorphism of abelian groups here. So anytime you have such a situation, if you have a cohomology theory, generalized cohomology theory, if you can write it as a set of homotopy classes of maps from your space into something, this space is called the classifying space for your theory. So you can summarize Atiyah-Jaenich by saying that, basically by saying that, yes, Fred H is a classifying space of K theory. That's what the result is. Fred H is a classifying space of K theory. Okay, so if you find the classifying space of your cohomology theory, you have done a good job for sure. So now let me roughly explain how to go from left to right, and then what is involved. I'm not going to prove it. I'll just give one idea of the proof, and then maybe at one stage later on if we have time.
So I am a bit confused with the statement itself. So the left hand side of the statement seems to depend on the choice of Hilbert space, right?
Well, all Hilbert spaces of separable and say, infinite dimensional complex are isomorphic. So it really doesn't matter. You can define a unitary equivalence between these two Hilbert spaces. So here I'm assuming compact. Maybe I should assume it's also separable, but it's not a big deal.
No, but that statement, I mean, like it will depend definitely on the cardinality of the Hilbert space, right? Like different.
What do you mean by cardinality?
Of the basis.
Well, yeah, Hilbert basis, right?
Yeah. So
I'm saying if X is separable, then it's enough to just work with separable Hilbert spaces. That's all. And then we know that all infinite dimensional separable Hilbert spaces are unitarily equivalent.
oh, all of them are.
Oh yes. Oh yeah. Of course, yeah. So the thing about Hilbert spaces that you should remember, one of the things you should remember is that, well, I say it like in a rhetorical way. All Hilbert spaces are isomorphic.
I thought it depends on the cardinality of the basis.
Of course, cardinality of basis. Yeah, I'm saying I fix the cardinality of the basis. Countable infinity, aleph naught. Yeah, I'm fixing that.
Exactly. So on the left-hand side, you're fixing cardinality of the basis. How is that choice reflected on the right-hand side?
Well, in this case, maybe I'm saying maybe I should take the separable or second countable, maybe second countable compact Hausdorff spaces.
Oh, okay. So
all manifolds, for example, are good for right-hand side. All CW complexes are good for right-hand side. Every reasonable space you can think of, they're good. Even Cantor set is good for right-hand side. A lot of things are good for right-hand side.
okay.
Right?
Okay.
So it doesn't matter. This Fred H, if you change your Hilbert space, as long as they have the same cardinality, so. But this is not the case, by the way, for example, Banach spaces, right? So if you take Banach spaces of dimension 3, there are uncountably many non-isomorphic Banach spaces of dimension 3, even dimension 2.
Mm-hmm.
Because you have all these like LP norms. They are not isomorphic as Banach spaces. They are not isometric to each other. But that's not the case with in Hilbert spaces. They drastically cuts down possibilities. It's an amazing thing that's true actually.
Mm-hmm.
So maybe I spent a little bit of time. Any other questions, by the way? Okay, so maybe I spend a bit of time explaining this map. So from left-hand side to right-hand side, there is this construction which is called index bundle construction. So what is it? First, assume that your family of Fredholm operators is such that dimension of its kernel is constant. Is such that dimension of, because we know it's a finite dimensional kernel, right? Kernel of f of x is constant. So assume, I mean, this is a big assumption, right? So the family is such that its kernel is, dimension of its kernel is finite. Then of course, because it's a continuous family, so let's assume X is connected, for example, then dimension of its co-kernel is also finite. Follows that dimension of co-kernel of f of x is also constant. I mean, it's finite, we know it is finite because it's a Fredholm operator, but because it's a continuous family, the index doesn't change, so dimension of kernel doesn't change, so dimension of co-kernel should not change, right? It's constant. then you can define a bundle, kernel bundle. So we elevate everything from numbers to level of vector bundles now, right? So the kernel bundle is so defined, maybe denoted by this, ker x. It's a fiber at each x is just, so this is sub-bundle of this trivial Hilbert bundle. So this is the set of all x and c such that c belongs to kernel of fx. So this is a bit of tautological construction, right? So we have this operator at point x, which is fx. It has a finite dimensional kernel. It's in this space. I just define my subspace to be just like. And because this dimension doesn't change and f is continuous, it's easy to see that this is a vector bundle. Okay. So, and you can do the same for co-kernel bundle. So then I just put it here like co-kernel of f, and x is again, I just define it as a sub-bundle of x plus h. I just take it the set of all x and c such that actually c belongs to image of f of x. So let me make my life easier. I just go to orthogonal complement of the image. Instead of taking co-kernel as an abstract sub-bundle, quotient sub-bundle or whatever, I just do it like this. Image of f of x, orthogonal complement. Again, these are finite dimensional vector spaces because of Fredholmness, and they move in a continuous way and their dimensions don't change. This is a vector bundle. So then index of f, by the definition, is the difference, formal difference between these two vector bundles. So this is kernel of f minus co-kernel. So as an element of K-theory, right? So because K-theory is just defined as group completion or growth in the group of these things. So it means that we just allow ourselves to take formal sums, and then we know how to add them, we know how to do operations on them. So that's K0. Okay, so that's the index. So of course you have to compare this with index of one operator t, which was dimension of kernel of t minus dimension of co-kernel of t. Compare these two things. You see, this is a more sophisticated version of this. It's a family version of this, right? But the same idea. So yeah, anyhow. So if your family is such that there is no jump in dimensions of kernels, then the construction goes like that. Now, what if there is jump? But jumps in dimension of kernel of f of x can easily occur. But then what happens is that in this case, you can show that you can find a projection of infinite p, such that first of all, index of p, I mean, okay, so p is Fredholm. And if you multiply, if you correct your x by this p, I'm sorry, f by p, family by this one. This has satisfies condition 1. And the thing is, within any homotopy, so that's where this idea of homotopy is very useful. Within any homotopy class of such maps, you can always homotope this to one of these things, okay? And then define, let index of f to be index in this sense of families. Now, one thing you should notice is that, so this P is self-adjoint because it's an orthogonal projection. So it's in, and if it is Fredholm, then its index is 0. So you're not changing the overall index of, even point-wise, you're not changing. This P is just one constant projection for all points, working for all points. Okay, so with this repair, you can actually define a map. Then you have a lot of things to check. You have to check that this is independent of choices you make. The map is injective. The map is surjective, and a lot of details. Actually, it's not an easy theorem because you need another very, very difficult theorem of Kuiper, which I won't talk about it right now, but we need all that in order to move on. But this result, that shows that Fredholm operators is a classifying space for K-theory, played a very, very important role in index theory from the beginning, in index theory for families, also in non-commutative geometry. The non-commutative analogs of this was very, very important. And so this theorem, you have to think about it all the time if you want to learn index theory, so that's very important. So I think it's a good time to stop because I have to charge my battery, and then after 5 minutes, we will come back. But maybe if you have questions, please ask.
So I have a couple of questions.
Sure. Yes.
Is there a finer version of this theorem where we can say maps, homotopy classes of maps to Fred K corresponds to something like rank K bundles over the space?
Oh, no. I don't think so. I don't think that would work because with this one, we are changing so much that at one stage, I think it's going to go wrong. I mean, first of all, rank K vector bundles, yes, that's a set. Complex rank K vector bundles, it's a set, but it's certainly not a group or anything in that sense.
Right.
Then I highly doubt it, but that's a good question. I highly doubt it. That's the case. Yeah.
And under this isomorphism now, so within K0 of X, we have this monoid of actual. So we take the group completion of this semi-group of just isomorphism classes of vector bundles, right? Okay. So if this semi-group sits inside the group, so
semi-group does not embed inside that. In general, it doesn't. You may have some collapse actually, I think. The map is, I don't think the map is injected, but that's okay. But maybe you don't mean that, right?
Maybe, okay, I'm just asking, okay, there, okay, let me just ask my question. So there is this isomorphism. What if I look at the inverse image of this, inverse image of the image of this map? So you have this map from the isomorphism class of vector bundles to the group completion.
Yeah.
And if I look at the inverse image under the isomorphism of the image of this map, what classes of maps do I get? What homotopy class of maps do I get?
On the left-hand side?
Yeah.
Yeah, on the left-hand side, you can construct a map. In fact, you just, I think, I can explain it when we go to recess, but the thing is, it's very important that, so let me explain this when we go to recess, because I have to erase some stuff, but I'm also worried about this charging stuff right now. So, but that, no, this, so, okay, so let us take a 5 minutes break and then we come back, right? So just